Welcome to This Explainer. Today, we're diving into what honestly might be the ultimate tech heist of the decade. We are talking about literally sneaking massive, frontier-level AI models right out of billion-dollar data centers and running them directly on the everyday consumer hardware sitting on your desk. And specifically, we're going to focus on a total paradigm shift, a breakthrough that completely rewrites the rules on how to run a massive LLM purely on a CPU, completely bypassing the need for a rack of insanely expensive graphics cards.
Okay, let's dive into this, because the sheer scale of what we're dealing with here is kind of hard to wrap your head around. 2.78 trillion. Yeah, trillion with a T. That is the number of parameters inside Moonshot's Kimi K3 model. Now, in the AI world, parameters are essentially the tiny little dials tuned during training that make up the model's brain. The more dials you have, the more the model actually knows. And this is a model so incomprehensibly massive, it normally requires a deployment setup that costs more than a literal house.
But here is the absolute kicker, the extreme contrast. Independent developers have somehow managed to run that exact 2.78 trillion parameter behemoth on a standard laptop CPU using just 8 gigabytes of RAM. No PyTorch, no massive deep learning frameworks, no CUDA, and absolutely no GPU required. Nothing. It is literally just a tiny C program reading the released weights straight off a hard drive.
To put this whole achievement into perspective for a second, the official deployment notes for a model of this size usually suggest using 64 top-tier data center accelerators. If you were to rent those, you're looking at roughly $48,000 a month literally just to turn the model on. And yet, this explainer is going to show you how some wild software engineering tricks have allowed developers to run it on basic, everyday consumer CPUs and standard RAM, hardware you probably already own.
Part 1, the hardware VRAM wall.
So to understand how they pulled off this heist, we have to look at why it shouldn't work. Historically, the brutal math of AI has been dictated by the VRAM wall. The golden rule has always been that to run a model, every single one of those parameters must sit in active memory at the exact same time. If you store Kimi K3's parameters the normal way at 16-bit precision, you need about 5.5 terabytes of memory. A top-end consumer GPU holds maybe 24 gigs, and an enterprise one holds 80, meaning you would need roughly 70 enterprise GPUs literally just to hold the model still in memory. That is the wall. Everything we're about to look at is a masterful trick to get around it.
Part 2, the mixture of experts.
So the crucial point is Kimi K3 isn't just one giant dense brain. It uses a clever architecture called a mixture of experts, or MOE. Instead of firing up the whole 2.8 trillion parameter network for every single word it generates, the model is actually split up into 896 smaller specialist subnetworks, or experts, per layer. When the model needs to generate a word, a router looks at the context and picks just 16 of those experts to wake up. And this extreme active versus sleeping ratio, this is where the whole hack becomes possible. Because it only wakes up 16 experts per layer, only about 3.7% of the model's parameters are actually doing any math for a given word. The other 96.3% are completely asleep. So the brilliant realization these developers had was simple. Idle weight does not need to be sitting in your RAM. I mean, if it's asleep, why load it?
Part 3, streaming from the SSD.
This realization completely shifts how we handle the hardware. We move away from RAM and instead leverage your computer's storage drive. Here's the incredible new CPU and SSD inference loop. First, they keep a tiny core of the model, the trunk, permanently in RAM. Then, step 1, the router picks the 16 active experts. Step 2, the engine reaches directly into your solid-state drive and reads just the 17 megabytes needed for those specific experts. Step 3, the CPU computes the math for that layer. And finally, step 4, it tosses that data right out of RAM and repeats the process 92 times across all the layers. You aren't holding the model anymore, you're streaming it.
But doing this requires some serious software discipline. If you try to stream a 1.5 terabyte file off a hard drive normally, your operating system will try to cache it, which will instantly cause your machine to freeze and start aggressively swapping memory. So, these engines use specific commands, like odirect on Linux, or completely turning off caching on macOS, to bypass the OS kernel entirely. The engine deliberately stops asking for memory before the OS tries to take it back. Like the developers say, a cache you do not control is not a cache.
Part 4, compressing the cache.
And this brilliantly illustrates the third major trick, managing the conversation's memory so it doesn't blow up the CPU's limited RAM. Normally, attention remembers every single word you've said, right? So the longer you talk, the more RAM it eats. Without compression, a full-length conversation with a model this size would need 310 gigabytes of RAM just for the chat history. But Kimi K3 uses KDA and MLA attention. It keeps a fixed-size summary and just rolls it forward. So instead of growing endlessly, that attention cache stays at a tiny 626 megabytes forever, whether you write a single sentence or a whole novel.
Part 5, the speed trade-off.
So we've bypassed the GPU, or streaming from the SSD, and we've compressed the cache. But what is the actual cost here? Well, now, what's really interesting about this is the bizarre reality of how the system performs. At an 8 gigabyte budget, you get a token roughly every 32 seconds. Give it 32 gigs and it jumps to half a token a second. Much better. But look what happens when you give it 58 gigabytes of RAM. The speed plummets to a dismal 50 seconds per token. Why? Because past a certain point, your OS actually starts fighting the engine for memory, paging out the critical core trunk of the model. Adding too much RAM literally ruins the speed.
Which brings us to the fundamental truth of running massive LLMs on CPUs like this. You cannot delete work. You can only move it. We tore down the memory capacity wall, for sure, but we just traded it for a storage bandwidth wall. To generate a single word, the engine has to physically read 17 gigabytes of data sequentially off your SSD. So the speed of your AI is now entirely dependent on the physical read speed of your hard drive. So let's be totally upfront about the honest reality for the user here. We are measuring speed in seconds per token, not tokens per second. Generating just a short paragraph, that's going to take you half an hour. A 500-word answer is going to consume nearly 6 hours of you just sitting there waiting. And before you even start, you need 1.7 terabytes of free SSD space just to store the downloaded model. So yeah, this is undeniably a technical demo right now. It is absolutely not a snappy, real-time conversational product. Part 6, the future of local AI.
Which begs the ultimate question. If it's so brutally slow, why are developers racing to build these CPU engines? Why is the community going crazy for this? Because of what it proves. It proves that frontier-class, trillion-parameter models are actually mathematically within reachable range for everyday consumers today. It exposes this massive blind spot that hardware isn't necessarily the primary bottleneck anymore. Our software defaults are. Plus, these projects act like compile-it-yourself textbooks in pure C, showing us exactly how these architectures work under the hood. And while it's too slow for chatting, it paves the way for something entirely new: autonomous, local agents. Programs that can just sit on your CPU and chew through massive reasoning tasks all night long, completely privately and for absolutely zero API cost.
Honestly, this quote perfectly distills the whole paradigm shift we're witnessing right now. The memory limit we had all taken for granted was not a property of the model, it was a property of how we were loading it. These developers didn't invent some magical new AI model. They just flat out refused to accept the established rules of the GPU data center and rewrote the loading mechanism from scratch to work on the hardware we all already own.
So, I'll leave you with this final thought as we wrap up this explainer. You now know that unconstrained, entirely private superintelligence can technically sit on your everyday computer right now, as long as you have the patience to let it think. So, if you had 1.7 terabytes of free storage on your machine right now, what is the first massive, complex prompt you would queue up to run overnight at half a token a second? Thanks for joining me, and keep learning.